Okay, this lesson is on friction. There are two kinds of friction we're going to be dealing with. There is kinetic friction. So I have a picture down here of a block on a desk. And so imagine if I'm pushing on some object on my desk and I feel some resistance against me, I feel some friction, and the box is, slipping across the surface, it's sliding, and I do feel a little bit of friction there. That would be like kinetic friction. And we'll define it this way. It's whenever there's slipping or there's relative motion between the object and the surface at the point of contact. Okay. And excuse me. Kinetic friction. I'll also use the example of like moving a dresser in your bedroom, right? So you're pushing on your dresser and it's sliding across the floor there. There's relative motion between the object and the surface at the point of contact. So that's kinetic friction. On the other hand, let's imagine you're in your bedroom and you're pushing on your dresser and you're giving it a good force. And I'm looking over here at this picture. You're putting some force on it, but let's say there's carpet in your room and it doesn't budge. So the object does not slip. Okay. When we push against that dresser, when we push against that object, we feel a resistance to that. There's friction there, and we call that type of friction static friction. So we'll just write for that no slipping. Okay. Let's start with kinetic friction. It's a little bit easier um, of the two, simpler to grasp in this case. Let's come over here. So kinetic friction, we can we have an equation for it. So the magnitude of the friction force, if it's kinetic friction, is equal to mu sub k times Fn. And whoops, this should say Ff. This is the friction force, which is in newtons. Okay, this symbol here, this is mu. It's a Greek letter. And the way that you could write it is like a U, and there's like another little stick here um, on the other side of that. And so sometimes if I'm writing it fast, it might look like this, which kind of looks like a weird looking M, but it's not an M. It's mu. It's more like a U actually, but it's a Greek letter. Um, and then it's got a subscript of K. So this is the coefficient of kinetic friction, where there's no units for that one. And of course, we know about the normal force on the object. It's an R. Okay, which is also in newtons. So let's talk about a little bit about this friction. Um, what increases the friction, the kinetic friction on an object? So I want you can pause the video and just think about it. If you're pushing against your dresser in your bedroom, you can kind of think of two factors that increase that friction, that affect that friction. And the first thing that students will tell me in class is the weight, the weight of the object. So if your dresser has a lot of mass to it, then it's going to offer more friction when you're pushing against it. If it's sliding across the room, even so, the more mass it has, the harder you have to push to get it to move. And I'm comparing something like a box on the floor, a couch, versus like a refrigerator. Sometimes I'll have to move my refrigerator to get behind it, and because of how heavy it is, it makes it very difficult to move. There's a lot of friction um, as it's sliding across the floor. So weight is a big part of that, which is where that Fn comes from. Because think of some object on the floor. The normal force is the amount of force that the ground is pushing on the object. And so the more weight, the more gravitational force there is, the more mass, uh, Fn would also increase. So that's that factor there. There's still another factor, which is this coefficient of kinetic friction. So Again, what increases the friction on some object as it's sliding across the ground? Well, it's the two surfaces that are in contact. If you're sliding your dresser, and let's say your bedroom is tile floor, right? So it's a little bit more slippery. There would be less friction between those surfaces, your dresser and a slick, tile floor, versus like a carpet. So your dresser is moving against a carpet. There's going to be a lot more friction just because of the types of surfaces that are involved. And this number ranges from 0 to about 1, and you could look it up in a table. Um, in our textbooks, we have some values for it depends on the surfaces that are involved. For example, like wood on wood, ice on ice, or rubber on concrete. If it's ice on ice, that's going to be a very low number, something really close to 0, 0.03 or 0.04, something like that. For wood on wood, it might be like 0.2. So there's more friction there than ice on ice. But then for something like rubber on concrete, well, that number gets closer to 1. And I don't know the number at the top of my head right now. Actually, I have a graphic here. So let's see, rubber on concrete. Right now we're looking at the kinetic friction. So they give us a value of a 0.7. And we'll talk here about static friction in just a bit. Cool, so that's coefficient of kinetic friction. It's a number that's determined experimentally, as we'll see in a few days. Cool, let's jump right into an example with kinetic friction. So we want to imagine that this thing is slipping across the surface. Mass is 8 kilograms. The coefficient of kinetic friction is 0.55, and we're pushing on it with a force F1 is 46 newtons. Okay, and so what is the acceleration of the block? And we are giving you that it is sliding. It is slipping. So first thing we should do in these cases is let's draw a free body diagram. We have mg, we have Fn, we have our pushing force F1, and it's starting from rest and it is sliding. We are going to say that there is friction here, maybe make it a little bit smaller, and we'll say F. So if it's going to accelerate, it's going to be in this direction. And so we will use Newton's second law. We only want the forces that have anything to do with this acceleration. This will be F1 first minus F equals ma. And before we substitute, we recognize that this friction force has to be kinetic friction. And so, we said that that is equal to mu sub k times Fn equals ma. Well, it's not always true that the normal force is equal to mg, but it is in this case, right? So we can also say that mu sub k times Fn, well, Fn we're going to substitute mg equals ma. And we're solving for m. So the last thing we can do here is just say something like this. And as usual, I don't have a calculator in front of me, so let me get one real quick. Excuse me. Now, keep in mind you can't divide the m's, right? So those have to stay. This is 46 minus 0.55. mg is going to be 80 over 8. So we'll just type this right in. We get 0.25 meters per second squared is the acceleration. All right, let's keep going. So let's say we have that same block. Excuse me. Let's say we have that same block and it's sitting there on a table or on the floor. Is there friction on the object? So think about that for a moment. If you draw a free body diagram, here's mg, here's Fn. There's no friction on this object because if you put a friction force on this object, that would imply that it's accelerating in that direction. Um, yeah, there's no friction force on the object at that time. Let's talk a little bit about static friction. And so let me erase this. Again, let's go to the example of maybe your dresser in your bedroom. And here, I'll represent that with this picture right here. So you're in your bedroom and you're pushing on your dresser, right? And let's say there's carpet, so it's going to have a lot of friction on there. You're standing there and you're pushing to the right, let's say. Let's call your force F1. Sometimes you might have noticed in your past, you've pushed on some object, you push on the dresser, and it doesn't move, right? And let's say you push with 1 Newton of force, okay? And I'm going to draw a free body diagram here. And you're pushing with a little bit of force, maybe it's 1 or 2 newtons, 5 newtons, or whatever. Not pushing with very much force. Well, there's going to be some resistance pushing back against you. And there has to be because um, otherwise your dresser would accelerate, right? If there was an unopposed force here, if your force was unopposed, it would start to accelerate. But you know that you push a little bit on it, it's not going to move. That means that there's a little bit of friction on there. And as soon as you let go, you take off your friction force, it goes back to this situation. I'm trying to get rid of these. So what's interesting about static friction, and this is before it starts sliding, right? It's just stationary there, is that it will meet the amount of force that you use on it. So let's say we go 10 newtons of force. It will match you, assuming it's not moving, it'll match that force. And so static friction is a little strange in that there's not an equation, there's not one equation that we can use to figure out what the static friction is. But this is the equation for static friction. The friction force, the magnitude of it, is less than or equal to mu sub s, which is the coefficient of static friction, again, no units, times Fn. And so, yeah, what it's showing you here is that there's a range of static friction that it could be. Like I said, it's going to match the force that you use against it, but only up to a certain amount. And that amount is given to you by this equation. So, yeah, we do have an example down here that we can kind of get right into. Okay, this is the same example from before, but we've added the mu sub s here. It's the coefficient of static friction, which, again, something that is determined experimentally, 0.65. And so we're pushing on a mass with force F1. So here I've drawn the free body diagram. And what we're going to do is we're going to calculate this equation. Oh, let me erase that. Should look like this. So the friction force, the static friction force, is less than or equal to mu sub s times Fn. Let's calculate what that is. Mu sub s is 0.65 times Fn, which is 80. We'll calculate what that is. 52 newtons. So what this is telling us is that the static friction is less than or equal to 52. So if we push on it with a force of 46 newtons, F1, okay, remember, static, this thing is not slipping. So we push on it with 46 newtons of force. This equation is telling us what the static friction force can get up to. It can get up to 52. It won't be 52 though. If we push on this with 46 newtons of force, it will match our 46 newtons of static friction. So that'll be 46. What this equation is telling you is that it can go up to 52. So let's forget this. What if we push with 54 newtons of force? What this equation tells us is that the static friction can go is less than or equal to 52. It can't exceed 52. So what's going to happen is 54 exceeds this amount, and so this thing is going to start to move. And when it starts to move, friction force is no longer static friction, right? Now it's slipping. And so the friction force we'd have to consider at this point, friction force is now kinetic friction, right? So we'd have to do it this way, which we've already calculated this. This is from the previous example. This would be 0.55 times 80. Which I think was 44. We didn't explicitly calculate this, but it was in the equation. Okay. So let's just jump right into another example. I think that's maybe the best way to do it. Yeah, we'll come back to this. It says if a problem statement includes the word minimum or maximum, which we're actually going to see in this one, then you can usually use the friction force is equal to mu sub s times Fn. And whoops, this goes over here. Okay, let's jump into another example. This object is at rest. We're pushing on it with a force Fp. The mass is 5 kilograms. Mu sub s is 0.35 and mu sub k is 0.3. Let's first draw a free body diagram for part A. G, Fn, pushing force Fp, and there is friction. Now, I don't know the magnitude of the friction at this moment, so I just kind of just drew it there. Okay, so question B, if Fp is 17 newtons, does the object start to move? And so here's the deal. We don't know right away if it's going to start to move. We have to calculate. We have to consider first the static friction, because our pushing force needs to exceed the maximum amount of static friction. And if we don't exceed it, it will not move. It'll stay as static friction. It'll stay put. If we do exceed it, then it'll start to move, and then we can figure out the acceleration. So it's kind of given away that it is going to move, but let's take a look. So I'm sorry, it is going to move in part C. So let's do part B first. So it says if Fp is 17 newtons, does it start to move? Let's calculate the force, the static friction force. And by that I mean not actually what it is, but what the maximum is. So the static friction force is less than or equal to mu sub s is 0.35, and the normal force is 50. Right, so remember, that's how we're calculating the normal force, is just mg. Can't always do that, right? But in this case, Fn is equal to mg. So we get a value of 17.5. Which again is not the static friction force. If we're pushing with 17 newtons of force, the static friction force is well within this limit here. It's going to be 17 newtons as well. So in other words, these forces cancel and the object will not move. So if we're going to answer this question, does it start to move? We would say no, it will not move. And so if you show this as your answer, you want to box in both of these, your calculation and then answer the question. Let's talk a little bit about this equation. So what is this equation telling us? It's telling us, again, that the static friction can go up to about 17.5 newtons. It doesn't tell us what the static friction is. We have to think about that. If we're pushing with 17 newtons of force, the static friction can go up to 17.5, and it's going to match us and it will not move. So let's think of it this way. What's the minimum amount of force, pushing force, needed to get this object to start moving? And think about that for a moment. In class, when I ask people that, the minimum amount of force, they might say, well, we just need to get a little bit larger than 17.5. So somebody first said 17.51 newtons of force. Someone said 17.501 newtons of force. And so, yeah, theoretically, yeah, anything greater than the 17.5 will exceed that static friction, and then the object will begin to accelerate. What if we push with 17.4999 newtons of force? Well, again, by the calculation, no, it will not. So it's less than this amount. If we push with this amount of force, the static friction force can still meet that. So according to the calculation, no, it will not move. And so here we want to distinguish between what we calculate and what you might experience in reality. So we're going to do a lab on this. In reality, it's a little bit messier than this. In the lab, you might see, okay, we push with 17.49999 and it doesn't budge. And again, we push with 17.49999 and it doesn't budge. And then you try it again a third time, let's say 17.499, and it starts to move. On the other hand, there might be a time where you push with 17.51 newtons of force and it doesn't move. It should move. You're exceeding that maximum static friction. But yeah, in reality, it's a little bit trickier than that. So maybe a better way to say this is the maximum amount of static friction, or the minimum amount of force needed to get it to move, is really close to 17.5, somewhere right in there, is maybe a better way to think about it. So that's just to show you the nature of friction. It's not an exact number. Okay, let's do part C. Part C, suppose we push with 20 newtons of force, which will exceed this maximum static friction, so it's going to start slipping, and we want to figure out what is the acceleration. So it'll accelerate in this direction. Now we can use Newton's second law. So the Fp minus Ff equals ma. And let's go ahead and substitute right now. So that's your pushing force minus, once it's slipping, this is kinetic friction. So all we did over here just doesn't mean anything anymore in part C. We're going to substitute the kinetic friction, mu sub k times Fn equals ma. And so mu sub k times mg is equal to ma. Whoops. So we can just divide by m. And now we'll just substitute it all. So, sorry, for part C we said 20. mu sub k is 0.3. mg is 50. And m is 5. That's 20 minus 15. Okay, let's just say it's 20 minus 15, which is 5 over 5. That's 1 meters per second squared is the acceleration. Cool. So that's just a quick run through of friction. And now we come back to this one here. So yeah, if we're asking for what is the minimum amount of force to get the object to move, or what is the maximum amount of static friction, yeah, sometimes we can just use it like this. Um, I write it like this, but I kind of think of it like this with an equal sign. So the minimum amount of force you need to get it to move is just over 17.5, and the maximum amount of static friction is 17.5.